Hello everyone. Today we are presenting our project synthesizing stereo 360-degree images. This is a team project proposed by An and Shiqing from the Department of Information Sciences and Technology at George Mason University. Our project is about enhancing user experience of 360-degree images. So here we will talk about the definition of 360-degree images. A 360-degree image is a panoramic image that surrounds the original point from which the shot was taken. Users can usually view this kind of images inside a head-mounted display, and they are allowed to switch their viewing directions of the panoramic contents by moving the HMD around. Currently, the 360-degree videos are supported in major video websites such as YouTube, Meta, or Vimeo, so we can see they are becoming more and more popular. And also, this technology is a great advancement in providing immersive multimedia experience to users. Although the 360-degree image is an advancement towards immersive multimedia experience, it is still not the real immersive multimedia experience. So here we will talk about what truly defines the immersive multimedia experience. Specifically, real immersive multimedia experience allows users to perceive the depth information of all the 3D objects in the virtual environment. And to achieve this goal, users are provided with stereo images. And specifically, stereo images are those images which contains two slightly offset images, separately shown to each eye of the user, as shown in the figure below. We can see the two cubes inside the images are not quite the same, and on the left side, the left subfigure is shown to the left eye of the user, and the right figure is shown to the right eye of the user, and in the perspective of the user's view, the users can see and feel the offset of this cube object, and the users can feel that this object actually comes in 3D rather than a 2D picture. And here is the situation of the current 360-degree images. So currently 360-degree images are recorded by only one camera. Therefore, it contains only one panoramic image, and this same image is rendered to both eyes of the users. Therefore, it is not a stereo image, and as a result, the users cannot perceive any depth information from the image. In another word, the users will feel like they are surrounded by a 2D panoramic picture, but they will not feel they are immersed in the 3D virtual scene. Here are some solutions for this limitation. One way is to stop the monocular 360-degree image recording and start stereo 360-degree image recording from now on. Specifically, instead of using one panoramic camera to record the image, we start using two panoramic cameras placed aside each other and start recording the image at the same time. So in this way, a pair of offset 360-degree images can be generated, and once this pair of images are displayed to each eye of the user, the depth information is perceived and the real 3D immersive multimedia experience is provided to the user. However, this method will double the equipment cost to record a 360-degree image, because it requires two cameras, And also, this solution does not truly solve the problem, because all the existing 360-degree images are still monocular, so a great part of those experiences are still poor for the user. In order to enhance the user experience in the huge amount of the already published 360-degree images, another solution is proposed. This solution aims to convert the monocular images into stereo ones with the assistance of machine learning technologies. Ren and Lee's team designed a deep neural network to first predict depth information in one image, and then with some handmade algorithm, the other offset image can be generated with this predicted depth information. And when this pair of offset images are rendered to each eye of the user, the stereo images is finally generated and delivered to the user. However, the network proposed in the related work cannot be directly applied to our case, because their network was designed for regular images, while in our case we have 360-degree images. And in order to feed a 360-degree images to the neural network, we first need to convert the image into an equirectangular image, as shown in the figure below. And we can see in the figure, in this equirectangular form, all the objects inside the picture are distorted to some extent. Therefore, if they are directly fed to the neural network, the predicted depth information will not be accurate, and then the further synthesized stereo images will also not be accurate. Therefore, the user experience of this kind of enhanced stereo images won't be promising. Inspired by the previous work, in this study we propose to take a step further. We aim to design a deep neural network to create stereoscopic 360-degree images from monocular ones. So a monocular 360-degree image is directly enhanced into a stereo one. And this solution does not need two cameras for the image recording, so the equipment cost is minimized. And most importantly, using this technique, all existing monocular 360-degree images can be enhanced into stereo images, so all users can enjoy real immersive multimedia experience. Here we talk about the implementation status of our data collection process. First of all, we have some requirements of our data quality. As we all know, data quality is crucial for the model training. So specifically, we have the following two requirements for our data. First of all, the data must be some videos that are panoramic. In other words, it must be 360-degree videos. And the second requirement is that the video must be stereo. In other words, each frame in the video must contain two panoramic images, one rendered for the left eye and the other one rendered for the right eye, and the two images should be a little bit different from each other. And here we talk about the data source that we used. We used the YouTube platform as our data source because it is the most popular video sharing platform worldwide, and it has abundant 360-degree videos available for us. And most importantly, it has a result filtering function that allows us to conveniently pick the stereo and the 360-degree videos to meet the data quality control that we need. Here is the implementation of the data acquisition step. We used a third-party library function named ytb-dl to download 360-degree stereo videos from YouTube. Specifically, we first manually selected 57 stereo 360-degree videos on YouTube, and then we implemented a script to automatically download them using the third-party library function one by one. And here is the implementation for the data preprocessing step. So basically, we implemented a script to randomly extract 40 frames from each of the video. And interesting thing worth noting here is that we can see that the 360-degree stereo videos have a different encoding format as shown in the two figures below. So one type of encoding format is as shown on the left side. We can see when we download the stereo video, we can see in each frame it actually contains a upper half and a lower half. So the upper half image is the image rendered for the left eye, and the lower half part is the image rendered for the right eye. And the other type of formatting is as shown on the right side in this figure. We can see that this figure is actually cut it up into 4 pieces. So the entire left part contains 2 images. So both images are actually rendered for the left eye. And the 2 images on this right half is both of them are rendered for the right eye. So basically, this script we wrote, it actually needs to check which format this video is using, and if it's using the format on the left side, then it will cut each frame in half horizontally, and the upper half will be used as the data for the left image, and the lower half will be used as data for the right side image. And if it's using the format as shown on the right side, then it will cut this image, it will cut each frame vertically, and the left half part will be used as the data for the left image, and the right half part will be used as the data for the right side. After the previous steps, we have collected more than 4,000 images for our training dataset, and among all these images, half of them are for the left eye rendering, which is shown on the left side, and half of them are for the right eye rendering, which is as shown on the right side.
This is the overview architecture of the GAN network that we use in our project. It includes 3 components: the generator, the discriminator, and the loss function. The generator receives a real image left and synthesizes the fake image right. The discriminator receives either fake or the real image, and it has to detect the real or the fake ones. The output of the discriminator and the generator will be input into the loss function. And the balancing interplay between the generator and the discriminator is the key to train the whole apparatus. In the following slides, we will discuss in detail the finalized structures of each component that have been used in our project. Next, let's discuss the architecture of our generator. We tried several architectures, and the figure below shows the finalized network structure. The main components of the network are 8 convolutional layers having orange colors. They are divided into 2 groups. The first 4 layers at the beginning of the network and the last 4 at the end of the network. Their main job is to convert the image left into the image right. There are two ways to connect between the two iron groups, via the residual connection or via a group of 4 red convolutional layers. The red convolutional layers compress features from the first 4 layers and supplement this information into the last 4 layers. Thus, the red group will increase the feature extraction and feature representation power of the network. On the other hand, the residual connection will facilitate the learning of the network. The last layer, colored in green, will produce an image from the result from the previous layer. Next, let's discuss the discriminator and the loss components of the network. One of the main challenges from GAN is that training the generator is very hard. This is because of the high memory requirement, but also because of the unstable nature of the network. That is, the gradient can quickly approach 0 or go to infinity, and in both cases, the training becomes impossible. And in order to solve this, the design of the discriminator and the loss function can play a decisive factor. So to deal with the challenge in training the GAN network, we follow solutions proposed from used in Yang et al. Paper. That is, we will use the Higgs loss to prevent the gradient explosion and vanishing. And in order to do this, the discriminator will not produce a binary decision, but it will produce a feature maps instead. Let's go into the detail of the structure of the discriminator and the loss function. The structure of the discriminator is described in the figure below. As previously discussed, the last layer of the discriminator is just a regular to the convolutional layer, and it is not a decision layer. As a result, the feature map output, let's call it fx, from the last layer will be input to the loss function. The loss function has two components, the Higgs loss and mean square error loss. The Higgs loss receives fx, which is output from discriminator, and the mean square error loss will measure the distance between the fake and the real image. And calculating loss is quite simple. It uses a ReLU function, and basically it's just a 1 minus fx if the input image is real, or the ReLU of 1 plus fx if it's fake. Even if it's simple, there's a theory behind it which explains how it can prevent the model from suffering from gradient explosion or gradient vanishing. The mean square error loss, its main role will be to maintain the overall structure of the image and prevent distortion, while the Higgs loss, it can enhance the realistic of the output image. The structure of the discriminator includes 13 convolutional layers, which color in orange, and 2 encoders. The encoder basically compress the feature maps and improve the feature representation power of the network. Let's discuss the result of our model training. So we set the alpha value at 2 different values, 0, 0, 0, 3, which means that the Higgs loss component play a minor role, and the mean square error loss play the major role. Second, we set alpha is equal to 0, meaning that there will be no GAN component, and the network basically become a regular DCNN. So we observe that training for alpha is equal to 0 is very fast. the model quickly converge. But when we adding the GAN component and the model, when it has to try to learn the underlying distribution of the data, the converging speed become much lower. For example, in this case, we training for 80,000 iterations, and the model is still learning, and it still cannot reach the level of the model that use only mean square error loss. So we think that is maybe because GAN is kind of unstable, so training it can be difficult. But anyway, we make the model learn, and it can somehow output some basic structure of the image. And the figure below showing that the generator loss slowly converge over time. The discriminator loss is almost zero all the time, and we did not show the beginning of the training, but basically the loss of the discriminator quickly reached zero. So in this slide, it shows some illustrative result, which is the output of the model when we set the alpha to 0, indicating regular DCNN, and alpha equal to 0003, which indicating a GAN network. And we can see that GAN have some noise in the image, indicating that it may have a little bit lower quality than the image generated using the regular DCNN. At the top row, it's clearly is more clear than GAN. So we think that the GAN may need some more training or more fine-tuning or a little bit change in the model architecture in order to improve the quality of the synthesized image. And again, theoretically, the GAN model should have higher output image quality due to the ability of the model to learn the underlying data distribution. Here is our conclusion and future improvement. First, we conclude that we have designed and trained a GAN model to synthesize stereoscopic frame for 360 videos, and we have evaluated the proposed network and compared the performance with a regular DCNN baseline. And here are the next one are 3 potential improvements for future works. First, we want to gather more data because for now the data is not enough to generalize the model. By collecting even more data, it will allow us to evaluate on the test set. Secondly, we want to improve the generator, either by changing its architecture or training procedure to reduce the noises in the images. And lastly, we want to increase the size of the output. Currently, the output is 64 by 128. This is because of the limited time in this project. Smaller output allow us to reduce the memory footprint and reduce the running time, which is the training time. Ideally, the output should be in 4K for 360 video. The solution, we could either cut the video into tiles and independently train on those tiles, or we could incorporate super resolution into our network structure. And that's it for our project. Thank you for listening and viewing.